Let's look at an example of using a derivative to find out information about a function that models motion. In this case, we have the function s of t equals t to the fourth minus 4t, and it models a particle in motion, where s of t is measured in centimeters and t is measured in seconds. Now we're going to assume that t is greater than or equal to 0. We'll be finding the velocity of the particle at 7 seconds. We'll be looking for where is the velocity of the particle equal to 0, and what does this represent. And then we'll be finding the acceleration when the velocity is equal to 0. So let's go ahead and get started. Now recall that velocity, v of t, is the derivative in position, so s prime of t. And just to make sense of this for a minute, remember that this is the limit as delta t goes to 0 of s of t plus delta t minus s of t all over delta t. And recall that the units for s in the numerator are centimeters, and the units for t in the denominator are seconds, so the units for our velocity here should be centimeters per second. And we can make sense of that by looking at the limit definition here. Now, we're not going to use that definition to find the derivative. We'll use the rules that we know and have developed. So s v of t, or s prime of t, is we're going to be using both the difference rule, the power rule, and the constant multiple rule. So that's equal to 4t cubed as the derivative of t to the fourth, minus 4 times the derivative of t. Well, t to the 1 minus 1 power is t to the 0, or just simply 1. So this ends up being 4t cubed minus 4. That's our velocity function. And now we're asked to evaluate that at 7 seconds. So v at 7 will be 4 times 7 cubed minus 4, which is equal to 1,372 minus 4, which is equal to 1,368 centimeters per second. And always include units in your answer when there are units in the problem. Okay, now next we're asked, when is the velocity of this particle equal to 0 centimeters per second? And what does this represent? So we want to find when our velocity, so when v of t, which is equal to 4t cubed minus 4 equals 0. Well, I can see that I have a common factor of 4. So let's go ahead and say that v of t equals 4 times t cubed minus 1 equals 0. Now, if 4 times the quantity t cubed t cubed minus 1 is going to equal 0, well, certainly 4 cannot equal 0. So the only way this could equal 0 is if t cubed minus 1 equals 0. So t cubed minus 1 equals 0. We can add 1 to both sides of this equation. So we get t cubed equals 1. And then we can take the cube root of both sides. So t equals the cube root of 1. Now, unlike the square root, I don't have a plus or minus when I deal with cube roots, because when you cube a positive number, you still have a positive number. When you cube a negative number, you still have a negative number. So the cube root and the cubing process both preserve the signs of the numbers. So t equals the cube root of 1. I don't need a plus or minus, and so this equals 1. So the velocity of the particle is 0 centimeters per second when t equals 1 second. This represents the particle having stopped moving. And this stop moving could be momentarily, but it is stopped precisely when t equals 1 second. Now, we want to find the acceleration when velocity is 0. So basically, we're asked to find acceleration when velocity is 0. Well, velocity is 0 when t equals 1 second. So acceleration, well, acceleration is change in velocity over time. So it's the derivative of velocity, which is the limit as delta t goes to 0 of v of t plus delta t minus v of t over delta t. Now the reason I went ahead and wrote that out is to focus on units. So the units of my numerator are velocity units, and we saw that our velocity units are centimeters per second, and the units for my denominator are seconds. So the units for my acceleration should be centimeters per second, or you could say centimeters per second squared. Either one would be fine. So notice that acceleration is the derivative of velocity. So we could kind of look at it this way. Acceleration is the derivative of velocity. And so we're taking the derivative of s prime of t, which means that we really, in essence, acceleration is the second derivative of position. So anyway, let's go ahead and find the acceleration when velocity is 0. So our acceleration function, go up and we remind ourselves what our velocity function is. Our velocity function is over here. It is 4t cubed minus 4. So what we want to do is we want to take the derivative of 4t cubed minus 4. We want that derivative. So our acceleration function, using the power rule and the constant multiple rule and so forth, will have 4. Then the derivative of t cubed is 3t squared minus, and the next term, the 4, is a constant, and the derivative of a constant is 0. So we end up with our acceleration function being 12t squared. Now, we have our acceleration function. We can go ahead and find the acceleration when velocity is 0. That is, remind ourselves, when t was 1 second. So acceleration after 1 second is 12 times 1 squared. So that would be 12. And then don't forget your units. You can either say centimeters per second, or you can just say centimeters squared. My preference is centimeters per second. In either case, we have found the acceleration when velocity is 0. I hope this helps.